talking about the Archimedes Principle. But before we actually state the Archimedes Principle, let us first know what it is. Because the statement is quite big, but the principle is really easy. Archimedes Principle basically talks of objects immersed in a liquid. If you have ever seen or if you have ever immersed your hand in a liquid or say water, what happens? When you start immersing your hand or say fingers in water, you see that the water level has started rising. So water is getting displaced. The more you immerse your hand, the more water gets displaced. Imagine if there is a container that is filled up to the brim with water. If you take some object and say a cube and just release it in water, what will happen? So, as per common sense, we'll say, okay, water is going to spill out. But that weight of water that has spilled out is actually the force that is acting on that cube. So that force is known as the buoyant force. The cube that is in water. So buoyant force is a force that acts upwards. Due to this buoyant force, objects seem of less weight in water. So let us perform one experiment to see what is buoyant force and how weight reduces in water. Now I am going to use a pair of scissors. This is the spring balance and a jar full of water. Now if you see, water is till here. Now just what I was telling you, if I start immersing my hand, you can see water has started rising. Can you see that? Yes. So what we are going to do is I'll just move the jar aside for a second. I'll first adjust the zero value of my spring balance. Attach this pair of scissors to the spring balance. Now how much does it weigh? So it weighs around 72 grams. Can you see that? 72 grams. Now I will start immersing it in water. So let us bring our jar full of water into picture. I'll slowly immerse the scissors. Pay attention on the value that we get on spring balance. Now as in how I've started immersing, you can see the weight is reduced. It is almost 42 grams now. You have to make sure that the pair of scissors do not touch the bottom of the jar. So this is how, because of buoyant force, the weight of the overall object was less. So this is the property of a liquid. So where did all this buoyant force, density, everything, where did it start from? So it started way back. So let's go back in time and talk of Archimedes. Archimedes was an inventor, a mathematician, a philosopher, and basically a very intelligent person. So because of his reputation, Archimedes once got a very different and challenging task. Greek king or emperor Hero once gave some gold to a goldsmith and asked him to make a crown for him. This crown in Greece is sacred. So the goldsmith made the crown and next day, after a few days, delivered it to the emperor. The emperor somehow heard some rumors that the goldsmith has cheated on him. The goldsmith did not use gold that was given by the emperor, but mixed that gold with some silver and just took some gold for himself. After listening to this, of course, the emperor was furious. He summoned or he called Archimedes and asked him to solve this mystery, because he did not want to punish if the goldsmith was really honest. Then Archimedes thought and he was going for a bath one day. After his cleansing process was done, he immersed himself, he got into a tub full of water, basically a bathtub. When Archimedes sat into the tub, as he started lowering himself into the tub, he saw that water from the tub was getting displaced. Curious Archimedes lowered himself even more to see what happens. The more he lowered himself, the more water was getting displaced. Something clicked Archimedes' mind, and it is said that he ran, getting up from the tub as it is, and started shouting, "Eureka, Eureka." That means, I found it. So what did Archimedes actually find? He found that the volume of the body, his body that was immersed in the liquid, was equal to the volume of water that got displaced off the tub. How did he relate it to the crown? What he did was, let me tell you one thing, the crown was to be like inspected, the overall situation, but the crown was not allowed to be hampered because it was a sacred crown. No damage was supposed to be done to the crown. So that was really challenging. So Archimedes thought that this has to do something with density, something with the volume getting displaced and these things. So what did Archimedes do? He asked one of the goldsmiths to make a crown of pure gold. You know that gold is denser than silver. So if you can see this formula behind me, density is equal to mass upon volume. So according to maths, if volume of displaced water is more, that means density is less, and silver has less density. So what he did was, he took the two crowns, identical, same in weight, and immersed both of them in water. One of the crowns displaced more water than the other. The crown made of pure gold displaced less water than the crown that was given to Hero by the goldsmith. So that proved that the goldsmith had cheated and the crown given to the king had silver mixed in it. So this is how Archimedes found out the overall situation. So we can say that also buoyancy can be related to density. If the liquid is more dense, the buoyant force acting will be more. If the liquid is less dense, the buoyant force acting will be less. So now, can you think why ships float in water? Okay, now after so much of talking, let's see what the Archimedes Principle is. That means the statement of Archimedes Principle. So I'll just move away. Archimedes Principle states that when an object is wholly or partially immersed in a liquid, it experiences a buoyant force which is equal to the weight of liquid displaced by the object. Now to relate the buoyant force, that means the upward force experienced, say, by this pair of scissors, if the water, see, let me bring it up. If the water would have spilled out completely, or if I say I immerse my hand like this, So you can see water is overflowing. So if I collect this overflowing water, the weight of this water that has come out, that has been displaced, will be equal to the buoyant force my hand will experience. Now there are many concepts like density we need to talk about, but as in how we do activities, we will talk about them one by one. So let us start with the activities. You also have these notes to refer to while performing the experiments. Let us get going. In the first activity, we will find out the volume of this ball using water displacement method and then verify it using the mathematical method. Now, just to tell you, I'll just remove everything from the window. You have been given two balls. One ball is lighter and that floats on water, and the other ball you can feel is hard if you press, and it sinks in water. So you have to take the ball that sinks in water. Now let us bring into picture this instrument. This is known as the overflow vessel. You can see this part, joint of it. Water will come down from here when displaced. Now I am going to pour water in the overflow vessel. Till the brim, or say till this point, to the edge of this joint. Okay, let some water come down. See what I've done, I'll show again. Let some water get displaced. Okay, let it rest. Now you can throw this extra water away. So I'll pour it in the jar again. I'll take the jar out of our frame. What we have done, just see, this ball, I have tied a thread to the ball so that it is easy for me to immerse it in water. Now I'll start immersing the ball in water and water will be displaced. We'll take this overflow vessel away. This much water, if you see in the container, was displaced. Now how do we know how much water is this? What is the volume? So now comes into picture the measuring cylinder. I will pour this water into the measuring cylinder. How much do you see the reading? I have to turn this to my side to see the reading. So it is 12. It is 12 ml. Even if it is not clear through the camera, you'll get to know when you do it by yourself. Now let us see using the mathematical method. I will take the ball out from water. If needed, you can take this hook out. Okay? Take out this hook. Take the same thread, or you may use some other thread as well. You know the volume of this sphere is 4 by 3 pi r cube, but r is the radius. Now we do not know the radius of the sphere, so there is one way to find it. Start from any point, put this thread and wrap this thread around the ball and join it here and leave this ball now. So this much is the circumference of the sphere. I will take a scale and we will measure how much this thread actually, what is the length of this thread. So it is 9 centimeters. This is how you will measure. Let me turn it to your side. This is 9 centimeters, the thread. Okay? So this is the circumference. Now we will find out the radius. Now let us see the volume using mathematical method. Now we saw using the thread that circumference of the ball was 9 centimeters. The formula of circumference is equal to 2 pi r. Substituting 9 here, so the radius we get is 1.4324 centimeters. Volume of the sphere, as we know, is 4 by 3 pi r cube. We substituted the value of r in place of r there, and we got the volume 12.31 centimeter cube, which is almost equal to the volume we got using this water displacement method. So why did not we get this exact figure is because you can see this is not as precise. So we cannot get 12.31. So this is how we can find out the volume of a regular shape, that is a sphere, a ball, using mathematical method and water displacement method as well. So now we will find out the volume of this irregular shape, this bolt and nuts together. We could find the volume of regular shape because it had a mathematical formula, but does that mean this does not have a volume? Of course it does, and we are going to find the volume using the water displacement method. So first of all, let me take out everything from the frame first. Fix these nuts on the bolt. You can see that I have tied the thread already to the bolt here, and then start fixing the nuts. I have fixed these nuts onto the bolt. We'll just keep this aside for some time. Bring measuring cylinder into picture. I will have to fill this measuring cylinder up to a certain reading and then immerse the bolt. So let us start. Let us see. I'll have to turn it to me. Yes. So I have filled it up to 15 ml, if you can see the reading here. Now let us immerse this bolt and nuts assembly. So gradually start lowering this assembly into the measuring cylinder. You'll be able to see that water has got displaced and the water level has risen from 15 to 18. It has risen from 15 to 18. So 18 minus 15 is 3. So that is the volume of this assembly. So we'll do some activities on density now. Density, as we know, is mass per unit volume. Also, we know the density of water is 1. So what does this mean? It means that 1 cubic centimeter of water, which is 1 ml of water, will be equal to 1 gram of water. So when we divide 1 gram upon 1 ml, it is going to be 1. So density of water is 1. Let us check if density of water is actually 1. To check density of water, we are going to need these many things: measuring cylinder, spring balance, a container, water, and this plastic bag. First of all, let us fill the measuring cylinder up to 25 ml. So we are going to take 50 ml of water. So if the measuring cylinder is 25 ml, that means 2 times we'll have to take 25 ml, which will be 50 ml. It's a little above 50 ml. I'll dispense that much. So 25 ml I'll pour in this container. Again we'll take 25 ml of water. And pour it in this container. So now we have 50 ml of water. I've taken this plastic bag. I'll pour this 50 ml water into the plastic bag. Okay, so you'll of course have to make sure that the plastic bag is not leaking. Take the spring balance. Every time you use the spring balance, you'll have to make sure that you adjust this 0 mark. So here you can see, I'll just keep this bag away for a while. Okay, now let's see. See, here you can see to adjust 0 setting. This is the scale which you will move to adjust the 0 mark, and the 0 and this pointer should be in one line before you start. So I'll have to turn this to my side. So I just lifted it, and now you can see 0 mark is and the pointer are in one line. Now let us take this plastic bag again. Make sure that you do not pull this hook because it is attached to a spring, because it is a spring balance. Now I am going to pierce this hook into the plastic bag. Okay, it's done. And I will lift it up. So you can see it is 50. Now you can tell that 50 grams of water, and we took 50 ml of water. So 50 divided by 50 is 1. So it is proven that density of water is 1. We saw the density of water is 1. Now we will find out the density of this regular shape, this ball. In the first experiment, we found out the volume of the ball to be 12 cc, 12 centimeter cube. Now we will find out the weight or mass. First we will adjust this 0 setting, bring it to 0, and there is a hook to this ball. Just pass the hook of spring balance through the hook and see what is the weight. It is 22 grams. It's 22 grams. So now what you have to do is divide 22 by 12 or 12.31 and find out the density. Just by guessing, what do you think? Will it be more than the density of water or less than the density of water? And if the density is more, what does it mean? Will that object sink or float? Of course, if the density of any object is more than the other, in this case water, that object will sink in water. If the density of any particular object is less than 1, which is the density of water, that particular object will float in water. The density of this irregular shape, that is the bolt and nuts. So let's start. So we have this nuts and bolt assembly. We'll keep it aside. Spring balance will be needed, but later. First we will do find out the volume of this irregular shape. For that, as you know, we need to fill water in the overflow vessel and let some water come out of it. Yes. Throw that water. Now take this nuts and bolts assembly and pass it or lower it into the overflow vessel. Keep it aside. There is some water collected in the container. Pour it in the measuring cylinder. It comes out to be 3 ml is the reading that is coming after immersing the nuts and bolt assembly into the overflow vessel. Now we'll find out the mass of this nuts and bolt assembly using spring balance. First of all, you know what is important? Adjustment of 0 mark on the spring balance. Then tie this thread to the hook of spring balance without pulling the hook of spring balance, because as you know it is attached to the spring. It is done. And lift the spring balance. Now let me see what is it is 26 grams. So 26 grams divided by 3. 26 grams divided by 3. So what do you think? Will this nuts and bolt assembly sink in water or float in water as per density? Now we will prove the Archimedes principle using this material. First of all, let us make the adjustment or arrangement of the overflow vessel. Pour water in the overflow vessel and discharge the extra water. It will come out of its spout and it's done. Now we will measure the weight of this ball, and it is coming 22 grams after the 0 adjustment of the spring balance is done. Now we will release this ball slowly. When it is attached to the spring balance, we will release it slowly in the overflow vessel and see how weight reduces, 1, and second, how water is getting displaced. So we'll start. Can you see what is the weight now? Let me turn it. It is almost 8 grams. From 22 it has come down to 8 grams, and you can see that after it is immersed completely, water is not coming out now. Okay, so now water is not coming out. So the water we collected from the overflow vessel in this container will be transferred to the plastic bag. We are going to weigh this water. After 0 adjustment again, we will weigh this and see it is coming 14 grams. Now do you remember the weight of the ball was 22 grams. In water it came up to 8 grams, and that means 22 minus 8 is 14 grams, and exactly 14 grams of water is displaced. So that proves the Archimedes principle.